Welcome you all. In this lecture, we will be learning about the topics like observables and residual symmetries. So, let's start. In a periodic crystal, every local or physical quantity, which in physics is called observables, because at least in principle it can be measured. So, can be measured. While in terms of quantum physics, observables in quantum physics states any local quantity, states any local quantity which is periodic in nature, which is periodic in nature. So let's take the example of charge density. So when you translate the charge density by one of the Bravais lattice, which is also valid for a complex crystal with a basis, so we can translate the charge density by one of a Bravais lattice. So this shows translation symmetry because this relation is valid in case of translation symmetry. Now, if we take the average of that quantity, that is of the charge density over a unit cell, since the unit cells repeats everywhere, so this corresponds to average overall the crystal. So the average is rho equal to 1 by Vp integration of rho r dot dr. So here this is a homogeneous microscopic quantity, and this thing is the volume of the primitive cell. So these physical homogeneous quantities can be scalar or as well as vector quantity. For example, let me write it. These physical homogeneous quantities can be scalar or as well as a vector quantity. For example, the polarization vector. For example, polarization vector. So when we apply an electric field, we create a local dipole in the crystal if the crystals have ions which can move. So the polarization vector can be represented by this equation, P vector so this is the polarization vector. This is the electronic constant in a vacuum. This is the susceptibility. And this is the applied electric field. So the above equation is only valid for isotropic system. So in a crystal, is only valid for an isotropic system. In a crystal, the polarization vector is related to the susceptibility and the applied electric field through a tensor through a tensor given by this equation, that is sum over J so 1 minute. This quantity here can be represented by 3 into 3 matrix. Sorry. So it is possible that direction of the polarization is different from the direction of electric field unless it corresponds to the direction of high symmetry. Let me write. It is possible that direction of polarization different from the direction of electric field, unless it corresponds to the direction of high symmetry. So in this equation, that is so here in this equation, applied electric field is the cause and this is the effect. While here summation over xj, it represents the intrinsic property of the crystal. Intrinsic property of the crystal means that how a crystal responds to the stimulus. So in general, properties can be represented by a tensor, and if the tensor is diagonal, for example, like this manner, so we can make comments that only in this case we are reduced to isotropic situation. So only in this case we are reduced to isotropic situation. So the value of the component of the tensor depend on the system of the reference. So this should be clear if we know about the vectors and tensors. Vectors remain same if we change the reference system, but the components change with respect to the new axis. For a tensor also it remains same, but the value of the component in a new system reference changes. Now let's take another example of tensorial dependence. When we apply a stress to a solid material, in response we have deformation or strain. For example, if we have here one solid material and here we have applied the stress, tensile stress. So when you apply stress to a solid material, so in response it will have deformation or strain. So stress tensor can be given by this equation. Here in this case, this is the effect and this is the stimulus. Now imagine that you have an origin here. Here there is origin, and you have a point at the position R. Let's take the point. So there is some point at a position R from the origin given by this vector. And when you apply an external force, then each point on the material moves with respect to an original position, and those displacement is given by the vector u. So when you apply the force, the deformation, then this point moves to the new position. Like suppose it moves to this position. Now from here to here, the displacement is given by this u vector. This is the point. This is the new point, new position of the point, new position of the point. So x1, x2 are the components of the position vector. Let me write. So x1, x2 are the component of the position vector, and u1, u2, u3 are the component of displacement vectors. We can write the equation of strain as in this fashion. So this is the symmetric tensor by definition. So this is the symmetric tensor by definition. Now if we have rotation, the new position component becomes something like this equation. Here, new position so here x1, x2, x3 are the components in old reference system, that is xj. Components in old reference system, and this thing x1 dash, x2 dash, x3 dash are the new component in a rotated in a rotated system. Of reference. So the new and old components are related by a transformation tensor, that is alpha ij. This is the transformation tensor. Now if we give the new reference system as so if these transformations such as if these transformations such as rotation, reflection, or a symmetry operation or symmetry operations, then it means then it means that nothing changes. So if there is a symmetry operation, the new component will be same as the old component. So if there is a symmetry operation, the new component will be same as the old component. So if alpha of ij represents symmetry operation, then the new substitutability will be equal to the old substitutability. So the system overlaps. So this is the new component which is equal to the old component. So by this equation, it means that we have a relationship between the component of the tensor. So it means that they are not all independent, so they depend on each other. So the more symmetry we have, let me write the more better. It means that we have a relationship between the component of the tensor So it means that they are not all independent. It means they depend on each other. So we can say that the more symmetry we have, the less number of components are independent. So the highest symmetry we can have is the isotropy. So the highest symmetry we can have is the isotropy. So in such case, tensor is just a one component in the diagonal and these are called residual symmetries. So the Breville lattice, which we used to represent a crystal, sometimes it's called diet lattice, and this will be the topic of the next lecture, and we'll study about the reciprocal lattice in the upcoming lectures. So for now, thank you.